And greetings, friends. We're going to get started this morning with just a reminder that PLC 7 is going on, and we're looking for Friday. Homework 4 for Tuesday.
It's broken now.
Oh, wow, it is.
You're not using it today. I'll glue it for you.
Well, we probably shouldn't glue it.
You don't think so?
I don't think it's going to hold. We should just construct something completely new.
Yeah, okay.
Yeah.
My apologies.
Well, the 6%, I mean, now we know why. What I'm going to do today is start getting on to ray diagrams for the lenses, and we're going to talk about converging and diverging lenses and ray diagrams. So let's get started on that. And at the end, we're going to go through something else that helps us figure out the focal lengths of lenses. And at the end, maybe we'll have time for a justification of why that's true. But in the meantime, I think it's going to be more efficacious for us to look at the result and then go back and look at some of the reasoning. So this is... well, we'll just leave that for now. What I'm going to do is we're going to start off with the ray diagrams, and then we'll see if we can get to talking about why the focal length thing works. Thanks. So let's start with converging lenses, and I want you to remember that all of the properties of the converging lenses are the same as the properties of the converging mirrors. So if we take a look at a converging lens, I mean, there are a few differences, and we're going to take a look at those too, but ultimately the images you get have the same quality, and that's what I was getting at last time in class. So the converging lens is this one, where it's thin in the middle and thicker, thin in the ends and thicker in the middle, so that it looks like this, okay? And if I take this thing here, right? Oh, wow, well, look at that. It's practically exactly the right size. If I take this thing here, I don't think you'll be able to see this, but if I take this thing here, you'll notice that a parallel incoming beam here becomes, oh, you kind of can see that, becomes curved upwards there, and if I push this up a little bit, now it's going straight through, and now I'm keeping the laser parallel, and so now it's going that way, so you can see that if I push the laser up and down, you can see what happens to the outgoing beam, like so. And that's why this is a converging lens. Let's take a look at what a converging lens ray diagram looks like. I'm thinking I need to make this a little bit larger. Okay, we'll go with that. Here's our optic axis, say. And when drawing the ray diagrams, this is going to be one of the differences. You have to extend this both sides, because what's the light ultimately going to do? It's going to pass through. This is a transparent medium. Yes, I know and you know also that whenever light hits a boundary between two media, there is going to be some reflection. However, we are neglecting that here because we want to concentrate on the light that's passing through. Now, I'm going to hold off on a little bit of this particular topic, but if you look at the curved surfaces, okay, if I look at the curved surface here, that would have a radius over here, right? The center point for this surface would have been over here, making as if I put a compass there and I'm drawing like this. This surface would have had the compass over here, drawing like this. Because each of these surfaces is made from a circle, each surface contributes a focal point. Okay, now, since we're dealing with radii that are equal and, well, even if they're not equal, we're dealing with something in which the index of the surrounding medium is all the same. Now, this would be different if I had this thing floating on water or something, right? If I took it and I had it floating on water like this, so that light was going from air into the plastic or glass, whatever the lens is, and then into water, then the focal lengths would be different sizes on either side. But since we are in air, the focal points are equal on either side. So I'll mark those as being here. And 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Did I say? Wait, 1, 2, 3, 4, 5. Yeah, 1, 2, 3, 4, 5, and it's this one. So those two are the focal points. I'll mark those with F. Like so. And we're going to go through and take a quick look at images made by objects which are in different places. Here we have a converging lens, so I'll start with the one we left off with this, right? So I don't need to do this one. The converging real image. We did that, we answered the 4 questions. All right, so I'm going to start with the object that's here and is inside the focal point. Since we've already done the real image for these, let's take a look at the virtual image that's going to get cast, because this is going to have the same exact qualities as a converging mirror had I put the object within the focal point. So here we go with that. We're going to take the green lever shows up. Let's try. Okay, so I'm going to take one ray in parallel, and I'm going to once again remember this is the thin lens approximation. So all my refraction is happening in the middle of the lens, right? It's going to happen in the middle. Despite the fact that, yes, there's going to be refraction at the first surface and then some straight line path and then refraction at the second surface. Yes, we understand that, but this is a thin lens, so we're going to make the approximation. This ray is going to go out through the focal point like so, going that way. This is what light does. It goes through a transparent medium, and that ray is a little bit hard to see. Let me darken that one in. A little better. Okay. That would be my first ray. And my second ray could go through the center, or I could choose the second ray to come from this focal point. Either way would work. I'm actually going to go ahead and draw both of them. From here up to there. Okay, and now out in the parallel with the axis. Oops, a little bit chunky there. Like so. Now on this side you can see they're diverging, and so we have to trace back in order to figure out where might these rays look like they are coming from. Because now in the case of the mirror, things were different. We had the mirror and we had the object, and we were looking from the object's side. And so we expect the light to hit the mirror and come back and bounce off and hit us in the eye, which it did. Sometimes we would find an image created here in the middle between us and the mirror. Sometimes we'd find the virtual image created behind the mirror. That's the exact situation we have here, because now with a lens, we're looking through at the light that's coming this way, right? The light that's coming this way is hitting us in the eye, and our eye is reconstructing those beams came from where? looks like they came from back here. Since this one is parallel, all I got to do is dot this one backwards a little bit. Okay. Using the dashed line, this is not light. This is a path that light was on. And so I'm going to do the same with this one here. Like that. And it looks to me like the image is going to be here. And we can just take a quick look at the 4 questions. For this image, we had to trace these back. We know it's virtual. It is on the same side of the lens as the object, or perhaps you might think of it as on the opposite side of us. So, whatever you might like to think of, maybe it's, we'll say it's in front of the lens. Being that the light is coming from this side, so we'll call this the front side, and then this would be the rear, the back side. That's the back side. It is magnified and it is upright, so we'll go upright first, magnified second. If we take a look at the workings of the mirror equation, we will find the mirror equation is identical to the thin lens equation. So we can check these results with the ray diagram and the 4 questions. We can check these with the thin lens equation, which was the mirror equation. Well, the good news is we don't have to know anything new. We don't have to remember anything new. This is all the same. The thin lens equation is still the same as it was. Well, I mean, it's still the mirror equation. So, if we take a quick look here, we're going to say we have a focal length. Suppose we have a focal length of 20 centimeters, and our object is at 15 centimeters. What kind of image are we going to find? Let's just take a quick look at that. Okay, we use the same sign convention for the focal length. If it's positive, it's a converging lens. It looks like this. Therefore, 1 over Q is going to be 1 over 1 over 20 minus 1 over 15. Right? Yeah. So what are we going to do here? There's something nifty that we can do, which is like multiply by 4/3. Or I could just go 60 on both of these. That's ultimately is what it's going to end up as. So if I go to 60 on both of these, I'm going to get a 4 and a 3, which is going to end up as a negative 1 over 60. And therefore my Q is equal to negative 60 centimeters. And that negative, okay, remember our sign convention with the mirrors was that if at least the sign convention I tried to imbue is that if the light was making an image where we didn't expect it. So for example, a mirror, we're going to have all the light on this side, right? It's going to hit and bounce off. If the image then is created by light over on this side, we called it a positive image distance. If the light bounces off, but then is diverging, and we find that the image is back here behind the mirror, we called that a negative image distance. It's a virtual image because there's no light back here. Okay, well, the same thinking is going to be okay for us here. The light is supposed to be passing through the lens. If it makes an image over here, we call that a real image with a positive image distance. But it didn't. It made it back there, and so we call this a negative image distance since it's a virtual image. okay? Virtual image has Q less than 0. Incidentally, I noticed I didn't draw my last ray here, which would have been the one that goes through the center. And that would have been there. Let's see if I can just do that one for you real quick. My third ray to choose here would be that one. Goes through the middle of the lens undisturbed, and had I traced that one back, yeah, it's gonna land up in there. It's gonna be pretty close. The ray we are not using with lenses is the center, the C ray, right? And a mirror, it's really simple because it comes from the center, bounces, and comes straight back. We don't have that particular, we don't really need that particular ray here, so. Okay, Q is -60. If I found the magnification, I would still go -Q over P, because geometrically, the reason I got this and the reason I get that are the same reason. So if this is still true, then that's still going to be true. And then I would go to say this is negative times -60 over 15. Right? Yeah. So this is going to be a negative, so that's a positive. And it's 4 times bigger. Which, mine's only 3, but still, it's magnified. So the same mechanical usage of the mathematical representation here, all right? Same exact way of using it, same interpretation that we had with the mirror equation when we applied it to mirrors, and it works exactly the same for thin lenses. All right, so we've done the converging lens real image and virtual image. The diverging lens works just like a diverging mirror. So I'll show you a diverging lens here. Where's the diverging lens? Oh, it's over here. Okay. You can imagine that oh wow. Seems like we got a little washed out here. Okay. Well, there it's back. Okay. You can imagine that I had a block of, I guess this is probably acrylic or something, right? And all I'm going to do is score it out into little smaller blocks. Here I'm going to take it out apart into 2 blocks here. And then if I take this block and I just make an arc in it, I get half of a converging lens and half of a diverging lens. So all I have to do now is take the other half, score that out, put the 2 pieces together, there's my converging lens, and then all I gotta do then is take these 2, put them together, and now I have my diverging lens, which is the opposite of the converging lens. It's thin in the middle, thick at the edges. Right? This is a diverging lens. And if you, let's see here. If you want to see that, then all we have to do is hold this here, or maybe I can put it right there and you can still see. Maybe I can put it right there. So if I take my incoming ray and it's parallel, notice what happens on the outside of it there. It's going definitely has changed direction. If I scoot it down, now it's going, where is it going? It's going approximately straight through. If I scoot down a little more, well, that's the reason I can't use this. Okay, so if I scoot down a little more and I'm here, then hopefully what you're seeing is that now it's going down that way and it's diverging away. If I come up here, it's diverging up. That was harder to see. Not sure why. Diverging lens. Nice big diverging lens here. Let's go. About like that. Optic axis straight through the middle. Marking off the focal points yet again. Let's go focal point, say there, which is 1, 2, 3, 4. 1, 2, 3, 4. Focal length about there. If I take an object outside the focal point, like so, and I can draw my principal rays yet again, with the adjustments that I don't go through the focal point on the same side as the object. I go initially in parallel and then, well, okay, I flip how I'm using them, let's put it that way. If I go in parallel, like so, and I'm going to still do the same thing and cause all the refraction to happen right in the middle of the lens. I'm looking now as if I'm coming out of the focal point, which is there and would connect here. So I'm going to dash in this line because I know I need it. I already know I'm going to trace this one back. So it's going to go like that. That's my outgoing ray. I have now the choice of either going through the middle of the lens undisturbed or aiming at the opposite focal point coming out parallel. I will draw both of those just for your own smiles and giggles. So let's take a look here. I'm going to aim at this focal point here. I'm going to aim the ray at that focal point so that it comes in here, hits the lens there. This is an incoming ray, and is now going to come out parallel. Okay, like so. So that now I can trace this back to about there, and my image should be here. Right there. Image should be there. If I take a look at the third ray, which is going straight through, it will be pretty close, at the risk of cluttering up this diagram immensely. Right, the one that goes through undisturbed is that one, and it's pretty close. It's hitting just the top of that. So those are the three rays. Remember, you only need two to find an image. We, like with diverging mirrors, oh, I didn't title this one, sorry, it's diverging lens. Like with diverging mirrors, we keep the same sign convention that the focal length is negative. So focal length should be less than 0 for a diverging lens. Same principle as operating with the thin lens equation, or we should start calling it something like the geometric optics equation or something like that. We're going to start operating with that. We have to keep the focal length sign in the equation if we do that. So if I do the same thing as I did before, but now the focal length, oh well, I should probably flip these because I drew it the other way. So let's make this 10 then. All right, and let's say that's minus 10. I got an object outside the focal length, but the focal length is negative 10 centimeters. So if I go through and do this, what I'm going to get here is a 1 over negative 10 minus 1 over 15. Okay, so I'm going to hit that with a 1.5, which is going to make it negative 1.5 minus 1, that's negative 2.5 on the top, and it's going to be 15 on the bottom. Let's see, 2.5, that should be 6, right? It's going to be 2.5 twice to 5, 3 times that to 15, so it should be, Q should be negative 6 centimeters. Okay, let's see and check and see what we got here. If this is 10, it's definitely within the focal point, right? It's definitely inside here. It should be a magnitude less than 10. It should be negative because it's on the virtual side. This is a virtual image. Oh, I forgot to do the 4 questions. Virtual image. What did I say on the other side? I said in front of the lens. This doesn't really matter so much with lenses. Since you're kind of used to it with mirrors, it doesn't matter quite so much with lenses. Anyways, it's on the same side as the object, virtual image. Upright and minified. So Q being -6, I think you can see pretty easily that if I look at the magnification, negative Q divided by P, I will get negative of -6, and P is 15. Right? So that's definitely small, that's less than a half. So it's positive something, so what is it? It's positive like 0.4 or something like that, say? I don't know. But it's definitely reduced, right? It's definitely reduced. Okay. So we've got those. Highly important that you know how to draw these ray diagrams, okay? Because on quizzes and on celebrations, if you're starting off and you're drawing a ray diagram for a lens and you're bouncing the light off right away, because the math is all the same, right? So it's like, that's not really a show of the physics. If you want to give me the physics, you've got to give me these ray diagrams. And they've got to be pretty accurate to the situation you're talking about. They don't have to be scaled necessarily, but they should be, like I'm doing here, reasonably scaled enough that you can tell by looking, right? You can tell by looking this is an upright minified image. So hopefully that will be something that you become flexible and fluent with. All right, so those are the ray diagrams. We've done those 3. What I'd like to do now is bring in another, well, actually, let's do, yeah, how about we do one more example? Let's do one more example before we do this. Yeah, let's do one more example before we do this. I had one here. Just remind me what I'm doing here. Okay, let's do this. Let's do this. In the same way as we did with mirrors, let's assume we have, for the example here, we have just the single lens. And we're going to say that the object, we know an object distance and we know a magnification. What did I want to say here with this? I wanted to say that it's, say, 16 centimeters from a lens. Or is magnified image has magnification of positive 0.25. Okay. So we'll say that the object is 16 centimeters away from this lens. We don't know what kind of lens this is. The image is magnified at positive 0.25. So we know that if I think about what 2 pieces of information the magnification is giving us, how does that help? Can you, from just this information, draw a ray diagram of what's happening? Okay, this means you got to figure out what kind of lens it is. Okay, so what kind of lens is this going to be? it turns out there's only one kind that's going to give you a magnification of positive 0.25. You got to think now about what does positive 0.25 mean? What does the positive mean? What does the 0.25 mean? All right, so come up with answers to that, and you be able to tell us what kind of lens this is, because there's only one kind of lens that's going to make this. The positive sign is indicating that the image is upright. And we kind of already have a couple of clues from the mirrors, right? That if we're dealing with a single mirror and I have an upright image, it's likely virtual. And there we go with getting washed out again. I don't know why that's happening. There we go. If I just back off. So what this means is that this is a virtual image. Okay, these are the steps of thinking you're going to probably go through in order to determine this. This is that it's a minified. Okay, just knowing that it's a virtual image does not tell us enough, because either lens will give us a virtual image, right? But if it's minified, that's going to be enough to tell us that this and this together, this has to be a diverging lens. Okay? The converging lens, if you've ever looked in a converging mirror, right, and you've looked at it up close, your face is always larger. And the same is true because you do it in a mirror, you can do it in a lens. If I do a converging mirror and I know that the virtual image from a converging mirror is always magnified, then I'm going to be able to say, since the lens does the same thing, if I get a virtual lens from a virtual image from a converging lens, it's going to be magnified, not minified. Okay? So the diverging lens is the only one that's going to work in this situation. Right now, we can go ahead and start figuring out, okay, do we know, is there a way for us to figure out things like, okay, well, what's the focal length of the diverging lens? I would expect that focal length to come out negative. So we want to make sure that that's going to happen. Where is the image? Okay, so if I take a look at this, I'm going to say, well, I know, again, that if I think about the magnification and it's negative Q over P, then when I look at the thin lens equation with 1 over P plus 1 over Q is 1 over F, I have a way to relate Q to P or P to Q, whichever you like, through the magnification, because I know what the magnification is and I know what the object distance is. Okay, so I can use this to say that Q is equal to negative m times P, and I can put that into here, which we've done before. 1 over P plus 1 over negative m times P should equal 1 over F. And from this, I would be able to factor out the P. P is given because I know how far my object is from the lens. M is given, we know that the magnification is, and so I'd be able to find F from this. Okay? Let's go ahead and finish that off. Okay? So 1 over F is going to be 1 over the object distance times 1 minus 1 over M. Something like this. At this point, it kind of like, why not put numbers in? Otherwise, I'm just going to flip these over and put a -1 on this. It's not that, right? At this point, basically, we can say we have a solution to this. I know that in math class, you'd get graded down for saying this is a solution to F, but that's just because they are testing you to see if you can actually take a reciprocal. I'm going to assume that we know how to take a reciprocal. So just like I would say that this is an answer to what the focal length is, I would also, during, say, a Snell's law problem, I would say that this is the answer to what an angle is. You can leave it as a sign, I don't really care. Anyways, here we go. We're going to do 1 over 16, and we're going to multiply by 1 minus 1 over a quarter. Oh, so this is 1 over a quarter, which is going to be 4. So this is 1 minus 4. And this is minus 3. So it's negative 16 thirds, which is good. What's negative 16 thirds? It's negative 5.3. Okay, which is good because I'm assuming that since I looked at the properties of the image and came up with the idea that it's a diverging lens, it's nice to see that I'm actually getting a negative in the focal length, which is what we were hoping for. We were expecting that to happen. From that, we could go through and find what the image distance is, right? And knock that one out, but I'm not going to spend time doing that. That's a fairly straightforward calculation. So the mechanics, like I was saying, of using the equations and using the interpretations are all exactly the same as we did for mirrors. Okay, so just take everything we learned from mirrors and the interpretation, but put in your mind, gosh, I have to modify the ray diagrams appropriately so that they are lenses now, and light goes through the lens. Okay, so that being said, there's one extra thing that we can talk about with lenses that we cannot talk about with mirrors. So, well, let's talk about it, because we can talk about it. Let's talk about it. And that is, we've discussed the two main shapes of lenses, and that is the converging lens, which is this one, and the diverging lens, which is this one, right? These are the two main lens types. But the question then comes as to, okay, but what if I had just half of a converging lens? Is this still converging? Is it diverging? What's going on? I have taken this converging lens and sliced it in half. So now what's the focal point? Does it still converge? What's going on with this? Well, we can test this out real quick. If I hold this here and I go like this, okay, I'm going to do my parallel incoming ray here, and I'm going to see, oh yeah, look at that. It is still kind of going up a little, and if I move to the top and I go parallel incoming, yeah, it's going to the down a little bit, right? So let's take a look at the difference between this and this. So that if I start down here on the down, here's my parallel incoming ray down here, and look, that looks like it's going a little bit sharper, right? If you kind of have in your mind about how far above, or how far after the lens it's going up to there, and I take half of this away, and we do the same thing. Now look, can you see that that's further away? However, it is still converging. So I've changed the focal length. And fair enough, right? The idea is that the curved surfaces are the ones that do the focusing, not so much the straight ones, right? That's not going to do any focusing. If a light hits this thing straight on, it's not going to know if the next surface is curved or not. It's just going to go in and go, right? So what we want to do is think about how to make a formulation such that we can have different radii on the different surfaces of the lenses. So, and this is why this is something we couldn't do for mirrors. Because light travels through the lens, we have two surfaces to work with as it goes in the lens and then out of the lens. We didn't have that with mirrors. So we can pay attention to the geometry of the two surfaces. So this will be the types of lenses. Types of lenses. All right, so we already have this one, and we already have this one. All right, so no problem. The question comes in, what happens if we have one of these? Or on the other side of that, what about one of these? Are those the same thing? Do these two things act the same way? That's a good question. I had it going this way with the plane side like that, right? And we knew that if it was parallel incoming, then it would go up that way. What if I flipped it around such that now it hits the curved side first? Okay? Is the focal length still going to be the same? Is it going to be different? What's going to happen? Here's my parallel incoming ray. Yeah, it's doing the same thing. Kind of has to, right? Light's path is reversible. So if it was going the other way, it would have ended up at the same place. So yeah, these two things are the same. So I'm going to erase this one because I'm going to have I need a different lens down there. And so here, what about if I had two surfaces and they had different radii? So suppose that I had one that looked like this, which was curved on the front side, but then not as curved. Oh, that looks too similar. Let's try that again. How about something like that? That's definitely different. Okay, good. What about something like that? Okay, so this is a situation where the lens has two surfaces of different radii, and now we want to know how do we deal with that? Okay, what is it that we're going to do, or how can we say, oh yeah, that makes sense? Okay, same thing would be true if I had one like this. If I had a lens that looked like this, and it was kind of half a diverging lens, like that, right? Or I could do something like this, where I've got still the same curvature, slightly like this. If I curve that side a little bit, if that helps, or something like that. All right. I don't know if that showed up quite as well as I wanted it to, so let me curve it a little bit more. Well, it's not quite there, but anyways, you get the idea. The point is, we're asking what happens when we have these different shapes. Okay, so what we're going to do with this, and this is where I can give you we're going to jump to the conclusion here. Something I don't really like to do, but I'm just going to jump to the conclusion here, and then if we have time, I can go back and kind of piece together why and how this is found. What we do is we use something that's called the lens maker equation. The lens maker equation was, I think, first discovered by Descartes. Same Descartes that did Cartesian. And it relates the focal lengths of the lenses to the radii of the lenses. So it looks like this. It's in nature, it's kind of similar to the thin lens equation, but it's a little bit different. So we're going to go like this. Like that. That's the thin lens, lens maker equation for a thin lens. Okay, so let's talk about what these quantities are. F is the focal point, or focal length, same as it has been. Now, N, this is a little bit cheating. So this is what you'll see in a textbook usually. It's just called N. It's a little bit of a cheat because this is typically just the index of refraction of the type of material you're using in the lens. Okay, so we'll just say this is the index of the lens. Okay, that's the index of the lens material. So if it's glass, for example, it might be 1.5. Now, in reality, this is a ratio of the two indices of the material that the lens is made of divided by the material that surrounds it, right? It's the ratio of those two indices, or of those two indexes, as physics people sometimes like to say. I take the index of the lens, I divide by the index of the material that's surrounding the lens. Since we are pretty much always in air, that's 1, right? The index of air is 1, and therefore this essentially turns out to be the index of the lens material. So, just thinking about that, really, it should be the ratio of N of the lens divided by N of the environment, or maybe surroundings is a better one. Let's put the surroundings. Okay, that's really what it is. So that if I took the lens and dropped it into water, we'd be able to deal with that, right? Okay, so what about the R's? These are the radii. That's the radius of the surface. The question is, which one's which? Okay, we've got an R1 and we've got an R2, so we need to come up with a convention. All right. Since we usually draw them from, as if light's coming in from the left, the R1 is the one light hits first. So if I had an object over here, for this lens here, then R1 is that one. That would be my surface for which I call the radius R1. Note that the radius then would be back over here and would be measured from here to here. This one would be surface number 2, and therefore its radius would be over here with the object. Now we're going to adopt the same sign convention as we did with the image. If the radius with the center point is over where the light goes, then we're going to call it positive if it's over on this side of the lens. It's going to be negative if it's on this side of the lens. Okay? So let me just kind of diagram that out here. So R1 is the surface that gets hit by light first. So I'll call that the first light surface. And then radius is greater than 0 if the C point, right? I always think of the radius as being related to the C point because that's where I put my compass in order to trace out this arc that's making the circle here, or the So if the C point is where positive image distance is, right, which would be on this side of this lens, then we're going to call that positive radius. Same side as the object. If it's the same side as the object, then it's a negative radius. So let me show you how this is working. If I take a converging lens, okay, we'll just take a look at this one here first. What I'm going to do is I'm going to erase these diverging lenses so that I can just work on doing a converging lens calculation right next to it. If I look at this one, then I'm going to say 1 over f is equal to, let's just say I made it out of glass, so my n is 1.5. Let's just say I've got 1.5 minus 1 for this. And now I have to multiply by the radius. So suppose that I've got an equal radius, right? I scored this side, took the compass over here, scored that side. Say it's something like 40 centimeters, all right? So say I've got a 40 centimeter radius and I just did it this side and then I did it this side. R1, right? R1 is the first surface and its radius is on the other side. So I'm going to do 1 over 40. That's a positive radius because that radius point, that center point is on the opposite side. It's where the image distance is greater than 0. Okay? Or if you like to think of it, opposite the object. Here on this side now, as the light goes through, it hits surface 2. Surface 2 has the center point on the same side as the object, and therefore it's a negative radius. But look, is what happening, I'm subtracting that. So I'm going negative, right? I'm going minus 1 over negative 40. Okay? Sorry, running into a little bit of room here. Okay? So I'm going 1 over 40 minus negative 1 over 40. But that means I'm going to say that this is plus and plus. And that's going to mean I get 1 over f equals 0.5 from my index minus 1 times 1 over 40 plus 1 over 40, which is 2 over 40. I'm going to take that 2 and I'm going to knock the 2 away with the half. And so 1 over f is equal to 1 over 40, and therefore focal length is equal to 40. All right? Let's take the exact same situation and do that for a diverging lens. Same exact 40 centimeter surfaces and center points and everything. And let's see what happens with a diverging lens. Okay, a diverging lens would have had 1 over f equal to, again, glass, let's say 1.5 minus 1. Now, if I look at the diverging lens, let's see here. If I look at the diverging lens, oh wow. I guess I should have been using this for a long time. If I look at the diverging lens, the surface number 1 has a radius over here. Surface number 1 has, that's R1. And therefore, this one's R2. If I'm doing the same type of thing, right, I'm putting an object out here on the left, the radius to the first surface, right, here comes the light, that's surface number 1, radius to the first surface is going to be negative. Radius to the second surface is going to be positive. So you can see what's going to happen here, I think, right? I'm going to take, you know what, I'm just going to rewrite this whole thing in this dark color, because that really worked a lot better. So I'm going to go 1 over f is 1.5 minus 1 times 1 over, my first radius is negative, minus 40. My second radius is positive, minus 1 over 40. So I'm going to get a 0.5 from the index, and I'm going to get minus 1 over 40 minus 1 over 40, but that's minus 2 over 40. And you see the same thing happens, but now I've got this minus sign in here. And so therefore it comes out as a negative focal length, and that's what we're assuming. That's what we're not assuming, but that's what we were waiting for. Okay. So that's how it works. You get a converging lens, you get a diverging lens, and you just make sure that you keep the same sign convention as the image has. Right? That's basically what all of that stuff is saying. Keep the same sign convention as the image. This isn't for mirrors, though, right? This is not a mirror thing, so this is lens only, okay? This is lens only. This is the only place this is going to show up is with lenses because that's the only situation, like I said, where light's hitting two surfaces. So you won't run into the situation where you're going to say, oh, well, what about a mirror when the object's over here and the image is positive if it's on the same side as the object? That's not going to happen for a lens. The lens is always, object is here, image is positive if it's over there. Image is negative if it's over here. So we keep that same sign convention and we work with the radii. Let's take a look at a couple of other examples here. What if I look at the one which has a flat edge to it? Okay. What if I look at one that has a flat edge to it? Oops. Can somebody hit Control Z? Darn. Okay. I messed that up. Okay, let's take a look at one with a flat edge to it, and we'll make it one like this. Same situation, my object is over here, light's coming in that way. Okay. So, I'm going to do, and I'm just going to assume the same glass refraction index. I'm going to do 1.5 minus 1, and I'm going to look at the radii, okay? So, the first radius is surface number 1, which is here. So where do I put my compass needle in order to make basically a completely flat surface? How far away is my compass needle? Where's the center point, in other words, to this? For a straight line, what's the radius? When you do that, make sure that you don't confuse radius with curvature. You want to say this is zero curvature, so you go, oh, maybe the radius is 0. No. You have to put the compass really way far away. It's got to be over here. That's where infinity is. It's right there, just in case you were wondering. So I put my compass there, and by the time, it's such a big distance, by the time I get over here, this is essentially flat the entire way. So 1 over R1 is 1 over infinity, because I don't really have a choice. That's going to be 0, which is nice. I'm going to subtract 1 over, I'm going to stick with the same 40 as the radius here. So now I look at R2, and I say, okay, where's R2? If it was over here, and I traced it, it would have been a positive radius, but this radius is definitely over here, so it's a negative radius. So I'm going to get, again, the same negative 40 as I had before when I did the other converging lens. And now look what happens. I get 0.5 from the indices, and this is 0 minus minus, which gives me positive, and this is now 1 over 40, which means that I don't cancel my half out, and so what happens is, right, essentially this doubles the focal length. The focal length of this one's going to be 80 centimeters. Which, by the way, is kind of what we saw when I had the two pieces together and I took one of them away. It didn't converge as quickly, right? If I had the two pieces together, it converged like it went up quickly, and then I took this one away, and then all of a sudden it was a lot slower. At least I could see that, but who knows what you could see? Because I could see that, and that's all that matters. All right, so that's what's happening with one of those. And so I'll leave the idea of the crescent moon-shaped one to you as well, where you're looking at one that looks like this with a fairly small radius, and then one that's got a radius that's definitely larger, right? So I'm going to have to think about, okay, how does this work? How does that work? Both these radii are positive, okay? Both these radii are going to be positive. And if I flipped it around, the same thing would basically happen. Because I would be changing the surface. This would be surface number 1. This is surface number 2, as long as light's coming this way. If I flip it around, then surface 2 becomes 1, and then you introduce a negative sign, but then you introduce another negative sign. And it's what I was telling you before, that as long as the lens is surrounded by the same medium, the focal lengths on either side are going to be the same, right? So I don't need to worry about a difference in focal lengths if I just flip the lens around. It shouldn't affect the focusing of the light or defocusing of the light if you save that. Okay, so there's that. I'll leave the example of that to you, and you can go through and convince yourself that one of these should still focus light. And you can make an estimate of, well, is it going to focus light as well as one that's a traditional looking one, or one that's half of a traditional looking one, or where is this one going to fall in the rankings here? All right. So, okay. So we got a little bit of time. Like I said, I don't really enjoy just throwing an equation at you because there's really no physics in that. There's no physics in just learning equations and then going, oh, I can apply an equation. That's engineering, right? That's what engineers are going to do. They have things to do with the outputs of their equations and things. We are trying to come up with these equations as a result of a model that we make, and really that's what our job is as physicists. We build the models, and then we analyze the models mathematically and say, I wonder if this works. If you're one of those physicists, then you're a theorist. And then if you're one of those who builds the model, represents the mathematics, and then tests to see if the mathematics actually represents some increment of reality, then you're an experimentalist. That's kind of how this works. So the question as to where does the lens maker equation come from, I can sketch this out for you. I will say that this is somewhat like getting thrown into an underwater maze with lead weights on your feet. The solution to the problem is not difficult. All you have to do is walk out of the maze. However, the implementation of that solution, getting to that, is rather complicated because you also then have to figure out how to move your feet with these weights on them, and you have to hold your breath, and you're wondering how long you have to hold your breath. So the steps are individually simple. Put together, it's a complicated thing. So my aim is not to overwhelm you with this, but it's to show you that this really is based in the analysis of the geometries of the situation. Okay, that's my goal here. So let me just sketch this out, and hopefully you can gain a little bit of insight into where this lens maker equation came from. Okay, let's go back to, for example, the crescent moon shaped one here. Well, actually, the first thing we should do is I should tell you what the approximation is. So let's do that first. This is basically the only approximation that we need. All right, and it's this one. I'm going to start with good old triangle. Okay? Remember, what did we say when we began, all the way back at the beginning? When we started looking at geometric optics, we said, well, this is a pretty interesting subject, but it would be a lot easier if we only looked at paraxial rays, ones that were really close to the optic axis. Despite what I draw on my ray diagrams, this whole analysis that we're doing is based around, we're taking rays that are not going in crazy angles. They're all going at fairly shallow angles. Okay, so if I call this, for example, maybe this is like well, it doesn't matter what this is. We'll just call this S and that D, and we'll call this H. So here's my right triangle. This is a fairly common situation in the geometric optics. Since we're dealing with such shallow angles, this is a little tiny angle right here, very small angle. And therefore, S and D are pretty close. We might ask the question, is D approximately the same as S? And you could say, yeah, probably is. If I shallowed that down, and I had my hypotenuse really way down here, you'd say, well, yeah, that looks pretty close. So how close is it? We'd say S is equal to D plus maybe some little bit, call it delta, okay? And if I want to find out how much more S is than D, then I just put my compass needle here, I take this, and then I just sweep upwards to find, D is a radius. Right? So I'm going to go up to here, and I'm going to ask the question, call that delta. How big is that? Okay, how big is delta? Well, because I can say that this is a right triangle, and therefore Pythagorean theorem holds, I should be able to write that h squared is equal to s squared minus d squared. Now, s being d plus delta, we can factor this thing. Okay? We can factor this into s plus d, s minus d. And we're going to see something right away. We're going to see that s minus d is delta. And s plus d is kind of like 2d or 2s or whatever you might want to call it, right? This is approximately, let's do it here, this is approximately 2d times delta. Right? Whichever one you want. S and d are pretty close, so it could be 2s, it could be 2d. Who quibbles? So delta then is approximately h squared divided by 2d. That's how much bigger s is than d. And if h is small, then we're talking about a second order quantity here in a small number. So delta should be fairly small for our analysis throughout this. Okay, having set that up, what I want to do now is say, if I look at this lens, the one that looks like this, is it easier to go out and around? I guess it is. Like that, if it's my crescent moon lens, then I'm going to think about the rays coming in from the left. Right? Here comes some light rays coming in from the left, and they're going to be focusing over here. Like that. Which means that my object distance, right, this is approximately like a p distance, and that's approximately like a q distance. I'm going to take this h, I'm going to make a triangle out of this. Right, so here's h, And if I just complete this triangle over on this side, like so, now you can see I've got basically the same triangle. So the question you might ask yourself is, okay, if I'm going to make a lens such that light emitted from here, all of it going to hit the lens experiences the same time, and all comes back to here because it focuses, then I need all these paths to be equal time paths. Okay, that's Fermat's principle. So if I do that, I'm going to say that I have an index over here, call that N1. This is also N1, but inside the material, maybe the material is N2. So the time it takes the light to go up here and then down there should be equal to the time it takes the light to go straight through. Okay? If I set all that up and I say, look, I've got a certain amount of time to go here plus a certain amount of time to go here, and that should equal the time it takes to go through the thickest part of the lens times the index, what's going to happen is I'm going to be able to show you that the lens maker equation essentially drops out from this. Okay? So, so using this approximation, I could say that N1 multiplying h squared over 2p, that's my object distance, plus N1 times h squared over 2q should equal N2 minus N1 times the thickness T of the lens, which is this thickness right here. Right? So in other words, the extra little bit that this thing traveled, the extra little bit that light traveled from here to here, and then from here to here, right? Remember, it's a thin lens. So from here to here and here to here, that little triangle is the same time as going straight through the lens. I can show you that the thickness is related to the difference in radii, and I think you can start seeing that we're going to get the lens maker equation out of this. Anyways, I will leave it at that and not trouble you any further. But I encourage you to think about the consequences of this. This is a great approximation, and like I said, it's us that come up with the models, and really what we want to do is understand the models, not just throw an equation and try to work the equation out. So that's our goal here. Though I failed at kind of doing what I just said I wanted to do, hopefully at least the mentality survives. And that is the conclusion of our class for this session, and in fact this week also. I will have some lab activity posted for you tomorrow, be getting that going. Get ready, you will be using the little laser that's in your lab kit. We'll be looking at the index of refraction of the acrylic half circle that you've got. So in the meantime, enjoy the rest of your day and the beginning of your weekend if you don't see this until then, and I will be back in class with you next week, and next week is the week prior to spring break, so we will have classes next week and then a week off. So enjoy your weekend, and I will talk to you soon. Ciao, everybody.